Hi, I'm Disleve Kanku. This is my final presentation for the KaggleX showcase. So my project is titled Arrhythmia Detection. This is a project that I've been working on with my mentor for the past couple months. So I'm very excited to present my project. Before I get started with the presentation, I'll start off with introducing myself. So like I mentioned, I'm Disleve Kanku, and I'm currently getting my master's degree at Northeastern University in Boston. Throughout my master's coursework, I've done a lot of research, and my master's thesis also involves using data science in the healthcare field, precisely in precision medicine. I've done a lot of work in building machine learning models and deep learning models to make predictions related to healthcare problems. So a quick introduction for the project. My project focuses on predicting or classifying arrhythmias into different groups. First off, what is an arrhythmia? Arrhythmia is defined as irregular heartbeats, and a timely identification of irregular heartbeats plays a pivotal role in preventing life-threatening cardiac events and ensuring optimal patient care. So basically, what we're trying to do, we are trying to classify irregular heartbeats into different classes, into different groups. And because we believe that early classification can help save a lot of lives and can help prevent life-threatening cardiac events. So a project summary. So for the data set, I use the MIT-BIH ECG data set. This data set consists of an extensive collection of ECG recordings. ECG, which stands for electrocardiogram data. These are heart signals, which can be recorded through various machines. And these ECG recording provides invaluable insights into cardiac activity. So with our data set, our ECG signals are recorded at a frequency of 360 samples per second, and we add a cohort built from our ECG data set. We explored 25 male subjects which were aged between 32 and 89 years old, along with 22 female subjects which range from 23 to 89 years of age. The project objective. The main primary objective of the project is to develop an algorithm which can robustly classify arrhythmia into different classes. Like I mentioned, the classes that we have, the five different classes we have the normal class, which is the standard and healthy heart rhythm. We have the pace beat class. This is a type of class which is characterized when heart rhythm are generated from artificial stimulations, for example, pacemakers. We have the right bundle branch block beat. This is right bundle branch block beats exhibits an abnormal pattern in the heart's electrical conduction system on the right side of the heart, while the left bundle branch block exhibits an abnormal pattern in the heart's electrical conduction on the left side. And then we also have a premature ventricular beat, which are irregular pattern originating in the heart's ventricles. Type of problem. So this is a classification type of problem, a multi-classification problem, because we are classifying five different classes. And this is also a supervised learning problem where data sets consist of target labels, and our model will learn from our training data and evaluate all that it has learned on the test set. Tools and frameworks. This is a list of some of the tools I've used. I use Python, I use WFDB, which is a waveform database software package. This plays a crucial role in handling and pre-processing ECG data. I use PyTorch for deep learning frameworks. I use Pandas, Seaborn, as well as Scikit-learn for my machine learning. So here are the implementation steps. My implementation step starts off with data pre-processing, where I clean and pre-process the ECG data. Feature extraction, where I use several techniques such as fast Fourier transform and discrete wavelet transform to extract features from my signals. Model development, where I built several machine learning models such as random forest, XGBoost, and support vector machines, just to name a few. I also explored advanced deep learning models such as CNNs, LSTMs, and artificial neural networks, and then which I then evaluated using several metrics such as precision, accuracy, and F1 score, just to name a few. So on this slide, I go through the data preprocessing or the signal preprocessing. So my data preprocessing involved two steps: a data segmentation and a peak detection technique. During the data segmentation, I basically divided ECG records into discrete sections and identify peaks. And peaks identify the R wave and the most distinctive features. Each segment includes a window before and after the R wave, and the data segmentation is basically important because this is vital for feature extraction and arrhythmia classification. During the data segmentation, I was able to transform raw ECG data into manageable segments, which can be easily processed for machine learning. During peak detection techniques, I use methods like the Pan-Tompkins algorithm, which are robust to noise and reliable for R-wave identification. Feature engineering. During feature engineering, I basically try to create features from the ECG signals. For example, features that we had was amplitude, width, and rhythm intervals, and peak information. So I collected peak information, for example, amplitudes. These were collected and converted into feature vectors, and this is important because it captures essential ECG characteristics and it also enhances the model's ability to distinguish arrhythmia. As well, I also believe that extracting relevant information such as peaks, width, and rhythm intervals allows to also reduce noise. Model training. So like I mentioned, I trained both machine learning and deep learning model. On this slide, I will go through the deep learning model performance. So the deep learning models which I train are artificial neural networks, long short-term memory, and convolutional neural networks. As we can see on the diagram right here, this is how my models perform for 5 different classes, starting for 0 being class 1 of normal beat, and two being I'm sorry, one being a different class. And most of my models actually perform really good with scores ranging from 95 to 99%. Evaluate, and then for my machine learning models, I use metrics such as precision recall and F1 score, and most of my models perform relatively well as well. And there's more information about that on my GitHub page, along with my Jupyter Notebooks file, which contains all the details on how my models perform. Here, this is a quick representation of how my random forest model performed. Data science topics which I apply for this project. Definitely, I learned more about machine learning models. I learned more about signal preprocessing techniques like fast Fourier transform and discrete wavelet transform, and in analyzing signals. I also got more comfortable in using deep learning models. What I learned from my project and from the data, I learned the effectiveness of deep learning models like LSTM and CNN in signal analysis. Also learned to recognize the importance of data processing techniques in order to improve model accuracy. Also learned the potential of machine learning in automating diagnostic processes. So to conclude my project, just in retrospect, this project successfully classified arrhythmias into 5 classes using machine learning and deep learning models. And for my acknowledgement, I want to extend my greatest gratitude to my mentor, Olayemi Oyeleke, for his invaluable contribution and guidance. I would also like to thank the whole Kaggle team as well as Ray Harvey for constantly communicating and keeping us in the loop. So here's a link to my project. This is the link to my GitHub, and here is the link to the dataset. And that is all. So thank you.